Hello, welcome to another module in this massive open online course. So, we are doing examples on convex optimization, alright, to better understand it through various examples, alright. So, let us continue this discussion. So, we are doing convex optimization problems. So, we are doing convex optimization problems, and in particular we are doing a few examples which I think will focus on or will illustrate how to formulate these problems and in fact how to formulate them as convex optimization problems, so that you can use a convex solver to solve these optimization problems, alright. So, let us look at yet another example, example number 3, that is we want to minimize this norm a x bar minus b infinity subject to the constraint that norm x bar or minimize x norm x minimize L1 norm of norm a x bar minus a x bar minus b bar subject to the constraint that L infinity norm of x bar is less than or equal to 1. Now, of course, if you look at this is a convex optimization problem. Because if you look at this, the L1 norm, this is convex and this is convex. So, you have convex objective, convex inequality constraint. So, this is a convex optimization problem, alright, and you can solve it, but we want to sort of how do I put it, recast it into a form that is more intuitive or more amenable to analysis, and you will see that this problem, which has this looks or is seemingly complicated, can be cast or can be recast in a very nice form, and that is as follows. We are going to do the following thing. So, you have a x bar, let us assume A is an m cross n matrix. Then you can rewrite this as follows. You have this A1 bar transpose, A2 bar transpose, this will be AM bar transpose x bar. So, this is your matrix A which has m rows, which I am denoting by A1 bar transpose, A2 bar transpose, AM bar transpose, A times x bar minus B1, B2 up to Bm, okay, and you are taking the L1 norm of this, okay, this whole thing, remember you are taking the L1 norm, which is nothing but the sum of the magnitudes of this elements of this vector, which is basically, you can write this as the sum of the magnitude A1 bar transpose x bar minus B1 plus magnitude A2 bar transpose x bar minus B2 plus so on plus magnitude AM bar transpose x bar minus Bm. And now what I want to do is I want to introduce a constraint. I want to introduce a constraint that is magnitude AI bar transpose x bar minus Bi is less than or equal to Yi. So, now what does this imply? This implies that minus Yi is less than or equal to AI bar transpose x bar, x bar minus Bi, which is in turn less than or equal to or which is less than or equal to Yi, okay. For instance, magnitude of a quantity x less than or equal to y implies that x lies between minus y and y. So, that is what we are using here, minus yi less than or equal to ai bar transpose x bar minus bi, which is less than or equal to yi. Okay. And therefore, now you have using the, now each of these quantities is less than or equal to yi. So, therefore, using the epigraph form you can write this as summation of yi's, that is summation, instead of minimizing summation of magnitudes ai bar transpose x bar minus bi, I can minimize summation of y1 plus y2 plus up to ym. Now, subject to the constraint that now we have this constraint, what is that, minus yi less than or equal to ai bar transpose x bar minus bi, which is less than or equal to yi for I equals 1 2 up to m. Okay, this is the constraint. And now you still have the other constraint. The other constraint is, remember, remains as it is, norm x bar infinity less than or equal to 1. Now, we have to also know that you can write this L infinity norm constraint also as a set of linear constraints, because look at this, what is this? This is L infinity norm. What is this L infinity norm? This is the maximum of magnitude x1, magnitude x2, so on, magnitude of xn, because remember x is an n dimensional vector, A is m cross n. So, this is less than or equal to n. So, the maximum of n quantities is less than or equal to n, that means each of those quantities is less than or equal to, that is, the maximum of n quantities is less than or equal to something, then each of those quantities must be less than or equal to the same thing. So, this means that you have, well, magnitude of x1 less than or equal to 1, magnitude of x2 less than or equal to 1, so on, magnitude of xn less than or equal to 1, which implies that minus 1 less than or equal to x1 less than or equal to 1, minus 1 less than or equal to x2 less than or equal to 1, so on and so forth, minus 1 less than or equal to xn less than or equal to 1. This you can write it in a compact fashion, this you can write it as minus 1 bar less than or equal to, this is component wise inequality, less than or equal to x bar less than or equal to 1 bar. Okay, is a component wise, that is 1 less than or equal to each component, minus 1 less than or equal to each component xi of this vector less than or equal to 1. And therefore, now, and further if you look at this, you can write this also as a component wise inequality. This you can write as follows, this you can write as minus y bar component wise less than or equal to ax bar minus b bar, which is component wise less than or equal to y bar again. Okay. So, this reduces to this equivalent representation. So, now you can write the equivalent optimization problem. And that will be, you have to minimize y1 plus y2 plus up to ym, which is basically minimize 1 bar transpose y bar subject to the constraint minus y bar less than or equal to ax bar minus b bar component wise less than or equal to y bar, minus 1 bar component wise less than or equal to x bar component wise less than or equal to 1 bar. Okay. And you can see, what you can see is this is linear, objective is linear, and constraints are also linear, or rather affine constraints, implies this is a linear this is a linear program, this is an LP. Okay. So, what we have been able to show is that interesting or seemingly complicated problem, which is basically minimize the L1 norm of something subject to the L infinity norm being lower than or less than or equal to something, can be written as a simple, as a very intuitive and an appealing structure. It can be reduced to a simple linear program, linear objective, affine constraints. Okay. So, that is what it is. So, it's and a linear program is much more intuitive, because a linear program is, I mean, the techniques to solve a linear program and various insights into the solution of a linear program are well known. Alright. So, from something that is very sort of difficult to understand at first impression, is we are reducing it to something that can be much more easily understood and appreciated. Alright. And although both these are, remember, equivalent forms of the same convex optimization problem. The original problem is convex, the recast problem is also convex. Alright. But the second form is much more intuitive and appealing. Alright. Okay. Alright. Let us look at another problem which is very interesting from a practical perspective. This is termed as network flow. This is a network, this arises in several, this is network flow, alright, and this arises in several optimization scenarios, correct. This is one of the most important kind of optimization problems that arises in various fields, such as for logistics management, supply chain management, etc. Alright. So, this is something that applies, for instance, in logistics, and the problem is very simple. Consider network. For instance, let us say we have a network of hubs. Okay. I am just drawing a simple network. These are, for instance, what you can think of these are hubs or sort facilities. So, this is our network. So, each of these nodes, this is a hub or a sort facility in, for instance, in the distribution network. For instance, you can consider a distribution network of an e-tailer, okay, an e-commerce company. Okay. With e-commerce and e-tailing gaining a lot of popularity, remember, to distribute these products you need a network of hubs or what are known as sort facilities, where you have a lot of these products that are bought into, sorted and dispatched to other hubs, and ultimately of course delivered to the end user. Alright. So, you have this network of connected hubs, alright, and there are products entering and then there are products leaving, or commodities which are entering and commodities which are leaving each hub. So, we have flows between these hubs. So, Xij, this denotes the, we can call it this as basically the flow from hub I or node I, and each flow has a cost. Cij is the cost per item of link or the path between ij. So, you have Cij, which is the cost per item, Xj is the number of items that represents the flow between node I and node j. So, these are basically your sort facilities, or basically this is a network of sort facilities or hubs. Okay. Now, in addition, what you will have is you will have a supply, correct. So, you will have external supply Bi So, if you look at each hub or each node, you might have something that is supplies or flows that are coming from other nodes, flows that are going to other nodes, and in addition you might have an independent supply Bi. Alright, so this Bi indicates the supply that is coming into node I if Bi is positive. On the other hand, its Bi is negative, it means that supply, alright, that commodities are leaving from that node. alright. So, Bi is the external supply at node I, it is positive, it is coming in, negative if it is going out, okay. This is the external supply at node I, okay. So, let us say n equals the number of nodes in the distribution network in this distribution network. It is a very elegant problem, n equals number of nodes in the distribution network. We have already seen Xij, which is the flow from node I to node j. Let me just define that again, because that is an important quantity. Flow from node I to node j. We have already seen Cij is the cost from item, cost per item from node I to node j. And let us denote the upper bound and lower bound of the, because remember each sort facility have a certain limit on the flows corresponding to particular, because there might be certain links or certain paths, right, which are where there are restrictions in terms of the flow, the total outflow or inflow of the products, all right. So, we want to have this flow corresponding to this flow, we have the lower bound Xij, Lij equal to lower bound and Uij equals upper bound, okay, which basically implies, it is very simple, which basically implies that each flow Xij has to be between Lij and Uij, okay. So, this is your lower bound and Uij is your upper bound, okay. And we will enforce another condition, that is, if you look at the total external flow B1 plus B2 for all nodes, the total external supply equal total external, this is a total flow, that is total external flow or you can think of this as net external supply equal to 0, which implies that total external supply equals total external demand. That is what it means is very simple, it is very intuitive, that is these products or commodities that are entering at some node are eventually leaving at some other node. So, it cannot happen that these commodities are entering, a large number of commodities are entering and only a few commodities are leaving, which means that these commodities are getting lost, or it does not mean that only some commodities are entering and a large number of commodities are leaving, which means commodities are somehow being magically generated, alright. So, it just means that commodities are entering and whatever commodities are entering at the various hubs are eventually leaving the network at possibly the same or different hubs, alright, that depends on the flow, okay. So, the net external supply, that is if you look at B1, B2, Bn, some of the Bi's are positive, some of the Bi's are negative, because at some point we have supply entering, some point we have the supply leaving, alright. So, but the net external supply, alright, must be 0, which means the total external supply equals the total external demand, which also means that if you represent this succinctly, this means that 1 bar transpose, if you look at this vector of supply vector, 1 bar trans B bar equals 0. Now, what we want to do is we want to formulate this network flow problem, which is minimize the total cost of the network, and it is very simple. Now, what is the total network cost? Total network cost is, if you look at all links I, j, alright, and j not equal to I. If you look at the flow Xij and the cost per item Cij, this is your objective, alright. This is the total cost. Total cost. Because if you look at this, this is your cost per item and this you can think of as number of items. Okay, so this is basically the total cost of running your distribution network. Subject to the constraint, now this is important, subject to the constraint, if you look at each node Bi, which is the total external supply, plus the total inflow, if you look at each node I, j equal to 1 to n, x ji, that is supply from, that is flow from node j to I. Now flow from j to I minus the flow from node I to all nodes j, this must be equal to. This is the important constraint. Basically says that total external supply at each hub and the total flow from all the other hubs to a particular node I must equal to the total flow of commodities or goods from node I to the other nodes. Alright, just is enforcing the constraint that none of the goods are either are not unaccounted for at hub I. Alright, they are goods that are not being generated or goods that are not disappearing. So the external supply plus the flow from all the nodes, right, must be equal to the external flows, sum of all external flows from any part, and this must hold for all particular nodes or all particular hubs in your, or all particular sort facilities in your distribution network. And we have the bounds that we have already seen, Lij less than or equal to Xij less than or equal to Uij, alright, that is your constraint. And of course, so this is your optimization problem, and if you look at this, this is your optimization problem, this is your optimization problem. This is your optimization problem, and you can see again linear objective. Linear objective, of course this must hold for all I, okay. This is basically linear or affine constraints. Again affine constraints. Implies this is also, and very interestingly, and you can see the practical nature of this problem. We are looking at a large distribution, and you can easily extend it to any number of, because the statement is general, so you can have a large distribution network with tens of thousands of hubs. What this says is, as long as the total external supply is equal to the total external demand, which generally holds, alright, and you have the links, the cost associated with each link, which is varying in a linear fashion, alright, with the number of items, you can formulate this as a linear program, and therefore this complex problem, minimization of the costs of a supply chain or cost of a distribution network, can be formulated as a linear program, and therefore convex optimization has several practical applications. In fact, this problem itself can be applied in a practical context to minimize the cost associated with a network, alright. So this is a very practical problem, and there are several such problems which have severe or significant practical relevance, alright. So we will stop here and continue in the subsequent modules. Thank you very much.